When a production line unexpectedly grinds to a halt, the immediate reaction is usually a scramble. Alarms go off, production targets slip, and human nature kicks in. People start guessing. Someone points a finger at the newest operator or blames the machine that jammed yesterday. But swapping out a part or retraining an operator based on a gut feeling is like taking aspirin for a broken arm. You might quiet the immediate complaints, but the underlying mechanical or procedural issue remains untouched, practically guaranteeing the exact same failure will happen again next week. To stop that cycle, quality control teams rely on the Ishikawa diagram, more commonly known as the Fishbone Diagram. It is a visual tool designed to cut through the panic of a breakdown and systematically map out every single potential cause of an error. By pulling the investigation out of people's heads and onto a whiteboard, teams are forced to slow down. They move away from throwing quick fixes at the wall and begin a deliberate, evidence-based search for the truth. Watch how this framework comes together. We always start on the far right, placing the main problem, the effect, straight into the head of the fish. From there, a central spine extends backward, anchoring the rest of the investigation. Off that central line, we draw our first two major diagonal branches. We have man, which covers human error, training gaps, or miscommunication, and machine, which tracks equipment malfunctions, worn parts, or faulty sensors. Next, we add two more critical operational categories. Method forces us to look at our standard operating procedures to see if our instructions are actually correct. Material investigates the raw inputs we are using, checking for things like poor ingredient quality or contamination. Finally, we complete the skeleton with the last two categories. Measurement accounts for instrument accuracy and calibration errors, while environment looks at the physical space, checking if factors like temperature or humidity played a role. In the industry, we call these the 6 M's. By categorizing our brainstorming into these 6 specific buckets, we ensure that no hidden variable slips through the cracks. Running an effective fishbone investigation requires a strict chronological sequence. Step 1 is writing down a highly specific problem statement and bringing a cross-functional team into the room. You want operators, engineers, and quality assurance specialists looking at the board together. Once everyone is aligned, the brainstorming phase begins. The team throws out every conceivable reason for the failure and carefully slots each idea onto the appropriate branch of the 6M framework. The goal here is precision. You do not just write down equipment failure and move on. You drill down into sub-causes, tracing that broad idea until you hit a specific mechanical flaw, like a pressure sensor drifting out of specification. But listing causes is not enough. The team then enters the verification phase, where they must pull maintenance logs, check calibration records, and analyze batch data to prove which of those sticky notes is actually responsible for the failure.
This step-by-step process acts as a massive operational funnel. It takes the chaotic noise of a dozen different theories and distills them down into a single, evidence-based roadmap for repair. Look at this completed fishbone diagram from a pharmaceutical plant. The red banner at the head clearly states our problem. A batch of tablets is failing its physical hardness test. The team started by mapping out the most obvious suspects. Under the man branch, they noted that an operator might be untrained. Under machine, they hypothesized that the compression punches were worn out or a sensor was malfunctioning. Then they expanded the search. Moving down the branches, they checked if the hardness tester's calibration was overdue under measurement and considered if the high humidity in the compression room was softening the product under environment. The actual investigative breakthrough happened over in the material category. By testing samples, the team found that the raw granules being fed into the press were holding entirely too much moisture. The data confirmed it. The team isolated the root cause to excess moisture in the granulation process, driven by an inadequate drying time. The corrective action was immediate: revise the drying procedure and retrain the operators on the new moisture check. If the team had relied on their initial guesses, they might have spent tens of thousands of dollars replacing perfectly good machinery. Instead, visual mapping successfully connected the physical symptom of a soft tablet back to a hidden flaw in the chemical recipe. Of course, the tool is only as reliable as the people using it. One of the most common mistakes is writing a problem statement that is entirely too vague. Another trap is bias, often seen when a team focuses heavily on the man category, trying to pin the blame entirely on personnel.
You also have to be careful not to list secondary symptoms as causes. If a machine is overheating, that is a symptom, not a cause. And if you skip the verification phase and fail to back up your final diagnosis with quantitative data, you are right back to guessing. But when executed correctly, the advantages are immense. The Fishbone Diagram provides immediate visual clarity for complex, multi-layered issues. It forces interdepartmental collaboration and zeroes in on the deep, systemic flaws that cause recurring downtime. Avoiding those initial pitfalls is the defining difference between applying a temporary operational bandage and implementing a permanent corrective and preventative action, known as a CAPA. Ultimately, the Ishikawa diagram is not a convenient drawing exercise. In highly regulated industries, it is a foundational driver of good manufacturing practice compliance, proving to auditors that you have a rigorous method for investigating deviations. By organizing thousands of potential variables into a clean, logical skeleton, structured analysis eliminates the chaos of a breakdown and replaces it with absolute operational control. If you want to master more tools for quality assurance and GMP compliance, hit the subscribe button below for our complete training series.